Okay, this is my quick probability lecture, start to finish, try to get you caught up on everything that you need. Probability, understanding what probability is first is really important. So probability is really the degree to which a chance event is likely to occur. All right, so chance event meaning something that is outside of our control, something that we can't really be skilled at, but really we're leaving up to what we would call chance or probability or luck. So we measure this as fractions, decimals, and percents. So for instance, if something has a 50-50 chance, that's 1 out of every 2. As a decimal, that's 0.5. And then remember to change decimals to percents, we just move that decimal to the right 2 places. So that goes boom, boom, which turns into 50%. Now we know that because those numbers are very, very common for us, but with something like this, that's a necessary conversion that we'll need to make. Examples, all right, we have rolling dice, 6 sides. We can't necessarily be a good dice roller if we're doing it the right way or in a fair way. Cards, if you were to shuffle cards, whatever you kind of pick from that card pile should realistically be up to chance or kind of luck, so to speak. What else? If you think about any of those kind of casino games, a lot of them start with kind of random chance. These are things that we're going to kind of focus on as we consider probability. Now, the first thing that we're actually going to discuss in terms of probability is something called sample space. The sample space of a probability set is the collection of all possible outcomes from a random experiment. So that random experiment is really talking about a chance event, right? Something that is happening by chance. And we're talking about the sample space as being all the possible outcomes. So if we needed to create a sample space for a single die, well, what are the possible outcomes for a single die? We have a 1, we have a 2, we have a 3, we have a 4, we have a 5, and we have a 6, right? So you've got basically those 6 sides would be your sample space. If you didn't want to actually draw this out, you could just include the numbers, a 1, a 2, a 3, 4, a 5, and a 6. There's your sample space. So if I'm talking about die, a single 1 die, we have 6 possible outcomes. That's my sample space. Now, if we needed to create a sample space for flipping a coin 3 times in a row, what are all the possible outcomes for flipping a coin 3 times in a row? Well, we could start to list them. Heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. I can list all of these different outcomes, but a way to create a sample space is actually going to be a tree diagram. So what we do with a tree diagram is basically we figure out the sample space within each outcome. So this would be like coin 1. That first coin flip, there's only 2 options. Our sample space is 2, heads or tails. Now for coin 2, we also have 2 outcomes, heads or tails. So to build a sample space off of the first, we could have a heads, then heads, a heads, then tails. Or we could go tails, then heads, tails, then tails. So really already for 2 coin flips, we have heads, 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 tails, tails, heads, tails, tails. That's a total of 4 different options or 4 different outcomes. So we started with 2 outcomes and then it jumped to 4 outcomes. Now, if we flip a third coin, well, we could have heads, 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 or heads, heads, tails, tails, heads, heads, tails, heads, heads, tails, 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 heads, heads. You can see where I'm going here. And this is building all of the possible ways to flip 3 coins. So coin 3, if I flip 3 coins and we count these up, we actually have 8 possible outcomes. Well, you can see the multiplicative property here. It multiplies on itself. 2 times 2 is 4, times another 2 outcomes gives us that 8, 4 times 2, right? So each time we add a coin, we double the amount of outcomes than we would have started with, right? And I can actually think about listing all of those off to the side now in kind of this order, right? Heads, 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 tails, heads, tails, heads. And this is a kind of detailed way to make sure that I am including every single option in our sample space. All right, so our sample space is a collection. So there's 8 total things. Sample space would be all of these different outcomes if I were to, list them off. Okay, which let me do that for you. All right, and this is me just using my sample space, my tree diagram over here to do so. This is always a possibility. Now, sometimes when you have more than just 2 options, it starts to get pretty complex, but there's sample spaces explained. Theoretical probability is actually us calculating the probability of some event. So this is where we actually talk about the number of favorable outcomes and out of the total number of possible outcomes. And this is what we would expect to happen over a period of time based on the mathematical chances, right? As long as everything is fair and of equal value. So for a coin being tossed, we have a 1 out of every 2. So this 2 is the possible outcomes, right? We're only flipping 1 coin. That's the number of outcomes, heads or tails. And only one of them would be heads. And you can actually see this notation here. This stands for the probability of flipping a head, probability of flipping a tail. All right, so let's actually look at, once again, die or dice. We have a 6-sided die being rolled. Find the theoretical probability of each. So the probability of rolling a 6. Well, think about our sample space. How many different options are there to roll? 6 different sides on a die. How many of them are 1? So if I were to think about this, this is a 1/6 chance. I have 1 that would be, the number 6 on the die. Maybe I should have used a number to have come up besides 6. That's the number 6 on the die. There's only one of them. And maybe I'll put that one side. And there's 6 possibilities. 1, 2, 3, 4, 5, or 6. Okay. What is the possibility of rolling a 1 or a 2? Well, let's think about our sample space. I'm just rolling 1 die, so there's still 6 options. But how many of those are 1 or 2? Well, this is actually the word or, for us in probability's sake, means to add things together. So there's 1, 1. So I have a 1/6 chance for rolling a 1 and a 1/6 chance for rolling a 2 because each of them has just one side. And so that gives us an added probability of 2/6, which we could have, of course, reduced to 1/3. Now, something I didn't do above that I should be in the habit of is making sure to convert these into decimals, 0.3 repeating, and convert that into a percent, because we might see these presented in many different ways. So 1/6, by the way, is 0.16 repeating, which is approximately 16.6%, which rounds up to about 17%. If you said 16% because you didn't round it, okay. Probability of rolling an odd. Well, let's see, how many odd numbers are there? 1, 3, or 5. Any one of those would be good. So that's a 1/6 chance, a 1/6 chance, and a 1/6 chance. So implied in here is this or, right? Any one of these, 1, 3, or 5. So that gives us a 3/6 chance, which we know is going to reduce to 1 out of every 2, which is a 0.5 chance or 50%. Get into the habit of being able to write them any different way. That's how we would find the theoretical probability, the chance, the chances, the degree to which it is likely to occur. All right, 50%, you think about that as about half the time. 33%, 1 out of every 3 times. 17%, 1 out of every 6 times, okay? We'll do another quick probability exercise. And in this one, once again, theoretical probability. So this is kind of what we would expect, okay? This is how we would calculate what we expect to happen based on the mathematical characteristics. We have a card being picked from a shuffled standard deck of cards. So here's our standard deck of cards right up top. We want to find the theoretical, the expected probability of the following events. Probability of picking a 3. Well, this time I have to consider how many different possible options are there in a standard deck of cards. If I counted all of the cards above, I'd have 52 cards. So therefore, our denominator for theoretical probability here is going to be 52. How many of those are 3s? Well, let's go up and count. I got 3 of spades, 3 of clubs, 3 of hearts, 3 of diamonds. That is a total of 4 cards. Now I could reduce those. And if I reduce those would get down to about 1 out of every 13. If I divided the top and bottom by 4. And if I turn this into my calculator by just simply doing 4 divided by 13, or sorry, 1 divided by 13 or 4 divided by 52, I would get 0.07, 69, blah, 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 blah. So that's going to approximately be, let's see, let's move that decimal over, about 7.6%. That's about 113 times. What's the probability of getting a club? Well, our sample space did not change. We're still talking about a full deck of cards. How many of those are clubs? Okay, count them up. What you would find there is that there's 13 of them. And you could actually reduce this to be 1/4. And if you think about it, is because clubs, there's only 4 different suits, so to speak, spades, clubs, hearts, diamonds, and they're all have an equal amount. So basically 1 out of every 4 cards is a club. That's how that reduces down. If you didn't do that and you type them both into your calculator, you would get the same thing, which is 0.25, which we know is 25%, which if we were to think about it, we know that 25% is about 1 out of every 4. So that gives us the likelihood at which something would occur. Now, of course, we have the word or again. So now we're going to be adding some things up. So let's add how many jacks we have, 4 out of 52. How many queens we have, also 4 out of 52. And how many kings we have, also 4 out of 52. So if we add those up, 4 and 4 and 4 is 12 out of 52, which we could reduce, but let's just go ahead and divide that to get 0.23, which is a lot more than that, 0.230, blah, 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 which is going to give us 23%. So a little less likely than pulling a club is the probability of picking a jack, queen, or king, which in a lot of games is a good thing. This is theoretical probability, or what we could expect to happen. Now, due to time, I'm going to pick back up and do another lecture on multiplicative property in sample spaces and talk about compound probability and eventually talk about experimental probability. That'll be in the next video.